Hi all, welcome to my presentation, a model study of multi-level signaling for high-speed chiplet-to-chiplet communication in 2.5D integration. I am Rakshith Saligram, graduate research assistant at Integrated Circuits and Systems Research Lab, working under Professor Arijit Raychowdhury at Georgia Institute of Technology, USA. This is the outline of my talk. So let's begin. Heterogeneous integration. Heterogeneous integration refers to the assembly and packaging of multiple separately manufactured components onto a single chip in order to improve functionality and enhance operating characteristics. Heterogeneous integration allows for packaging of components of different functionalities, different process technologies, and many times separate manufacturers. It increases system yield, alleviates memory bandwidth bottleneck for microprocessors, and addresses the challenges associated with slowing down of Moore's law. A general model of 2.5D integration systems used in this paper is shown. We have multiple chiplets on a common substrate, and the technology dictates how small the distance between the interconnects can be, which is generally called the pitch. As we expect, smaller the pitch, more the number of physical I/O, higher the shoreline bandwidth density, but also higher the crosstalk and interference between the channels. This article provides a design space exploration of fine pitch interconnects starting from channel modeling, S-parameter characterization, signaling methodology, and first order power and energy estimations. Let us look at some of the prior work in the areas of 2.5D and 3D integration technologies. We have the following: the COWOS, or chip on wafer on substrate from TSMC, comprises of ultra-thin interposers with through silicon vias, or TSVs. The logic dies are bonded through microbumps on a silicon interposer, forming chip on wafer. This structure is thinned so that the TSV perforations are exposed, followed by C4 bumps formation and singulation. The COWOS package is completed through bonding to a package substrate. This technology is successfully deployed in NVIDIA's Pascal P100, AMD Vega, Fujitsu's A64FX, etc. Intel's proprietary EMIB, on the other hand, uses thin die of silicon with multi-layer BOL interconnects embedded in an organic substrate. This will eliminate the need for TSV processing and eliminate the limit on the die size. Heterogeneous integration stitching technology, or the HIST, uses a stitched chip with fine pitch high density wires placed between the substrate and the chiplets. Unique compressible micro interconnects used reduce the effect of non-planarity. Foveros used in Intel Lakefield uses face-to-face die stacking approach, where TSVs are used to connect to the bottommost die to package, while face-to-face connections are done using microbumps. Signaling in these integration technologies is an active area of research. Generally, due to the availability of large area, use of parallel I/O is favorable compared to SerDes. Parallel I/O has less design complexity since it allows the clocks to be forwarded along with the data. The recently proposed and open source Intel's Advanced Interface Bus Protocol uses parallel I/O instead of conventional SerDes. One other problem with conventional SerDes is that higher order modulation schemes like PAM4 are not very successful due to long channels. In heterogeneous integrated systems, since the chiplets communicate over rather a short distance of order of few microns to a few millimeters, PAM4 is indeed a competitive signaling scheme. The key contributions of this paper include a building of comprehensive EM models of parallel I/O links and evaluation of NRZ and PAM4 schemes to get higher bandwidth and energy efficiency. To model the communication channels, we invoke a coplanar microstrip model for on-chip interconnects. This is a symmetric structure, that is, the spacing between the microstrips, or the pitch, is uniform and all the channels are of equal thickness and width. In this study, the middle channel will be the victim and the outer two channels act as aggressors, interfering with the signal on the victim. It has a dielectric material of height h sandwiched between the common ground plane and the conductor or the channel. The substrate discontinuity of the microstrip causes the dominant mode of transmission to be quasi-TEM. As a result, intrinsic impedance Z0, the phase velocity, the field variation across the channel becomes frequency dependent. The general constraints are given by these equations, and the chosen dimensions are tabulated in this table. We parameterize the channel pitch and the channel length and generate touchstone files for each configuration, giving a total of 100 configurations. The main disadvantage of coplanar microstrip lines is that it has higher radiation due to lower isolation and hence more crosstalk. The effect of coupling can be distinguished by looking at the E fields on the victim channel in the three cases of no aggressor, one aggressor, and two aggressors active. The magnitude of the E field at the receiver decreases across the three cases, indicating that the crosstalk is a major issue in fine pitch interconnects. Next, we see the transceiver system architecture. The first component we have is a channel. Here, we use bundled data clock forwarded channels. Each of the coplanar microstrip line acts as a channel. To improve area utilization, we propose single-ended transmission, which uses half the number of links as opposed to differential signaling. Also, to provide energy efficiency, we eliminate any equalization or clock recovery by forwarding the clocks. Thus, for a bundle of every 8 to 16 data signals, we have one forwarded reference generated clock. Once we decide upon the channel, we need to think of the type of signaling to be used on the channel. We use two types of signaling, non-return to zero and PAM4. NRZ, or the non-return to zero, sends a voltage of VDD to signal a 1 and a voltage of 0 to signal a 0. And PAM4 signals based on 2-bit symbols according to the table shown. A sample waveform for a given bit stream for both NRZ and PAM4 is shown here. The next components are the transmitters and the receivers. First, for the NRC system, since we are not using any pre-emphasis or equalization, the transmitter can be a simple buffer with the only constraint that it must be well sized to drive the pad capacitance on the receiver side. Similarly, the receiver is also a buffer which can be viewed as a high gain voltage comparator comparing the received signal to its own trip point voltage. The NRZ system is shown here. For the PAM4, the transmitter is a simple 2-bit DAC with a current mode driver, and the receiver will be a 2-bit flash ADC comprising of 3 high gain comparators and an encoder. The PAM4 system is shown here. The simulation setup is as shown, and the simulation is performed in Keysight ADS platform for 28 nanometer technology node. The transmitter consists of a PRBS generator, the output of which is electrically encoded to voltage. The transmitter has a transmit resistance of typical of 50 ohms and a pad capacitance. For PAM4, we use simplified IBIS AMI models along with the executables generated from MATLAB Cerdis toolkit, which can be used in conjunction with the ADS topology. We use a supply voltage of 1 volt for both NRG and PAM4. Channel is modeled in the form of 6-port S-parameter network, which uses touchstone files generated from the HFSS models. The outer two aggressor channels are connected to crosstalk generators, which generate out-of-phase signals to the transmitter. On the receiver side, we have the pad capacitance, but we eliminate the legacy termination resistance in order to reduce the power consumption. The receiver is a simple buffer for NRG and the MATLAB generated IBIS AMI model for the PAM4. We capture the eye diagram at the receiver to evaluate various properties of the received signal. The simulation is performed for different pitch and channel length configurations. Here we are seeing the eye diagrams at constant data rate for 4 pitch length configurations for both NRG and PAM4. For a given data rate, the eye opening increases with increasing pitch due to lower crosstalk, and it decreases with increasing pitch due to higher attenuation. But we need to note that the electromagnetics of the coplanar microstrip lines is much more complex than simple linear relationship between frequency of operation and the channel dimensions. The channel operating margin, or the COM, is a measure of channel performance and is defined as 20 log to the base 10 of the ratio of signal amplitude to the noise amplitude. It can be determined from the eye diagram also as shown in the figures. The minimum channel operating margin required for signal recovery at the receiver for NRZ is 3 dB and for PAM4 is 9.5 dB. For PAM4, the average of COM for the 3 eyes is taken. What we try to do is, for each pitch length configuration, we determine the highest frequency that can be achieved while still maintaining the COM requirement by setting an optimization goal over a suitable frequency range. The intensity plot of the highest possible frequency versus the channel dimensions is shown for NRZ and PAM4. In ideal scenario, the data rate increases with increasing channel pitch and decreases with increasing channel length. Here, with design space exploration, we need to look at the general trend while considering the maximum frequency of operation is controlled by the electromagnetics of the channel, effective dielectric constant of the substrate, characteristic impedance, resonant frequencies, etc. The highest frequency of operation for the NRZ system is 2.35 GHz and for PAM4 is 1.49 gigasymbols per second at a constant bit error rate of 1 e power minus 50. Looking at the power estimations, the main component of the system is the PLL. We consider a non-differential 5-stage VCO along with the phase frequency detector and a series of TSPC flops in TG muxes acting as frequency divider. If P bias is the power of the bias circuitry, CPFD, CDIV, and CVCO are the total capacitances of the phase frequency detector, frequency divider, and the voltage control oscillator, then the PLL power is given by this expression. Next, we look at the NRC transmitter and the receiver. Assuming a single-ended voltage mode transmitter, the driver is a buffer circuit which needs to drive the pad capacitance. If CPAD is the pad capacitance, then the transmitter power for NRC is given by CPAD times F clock times VDD square. The receiver power is also given by similar expression, except that the load capacitance is just another buffer. Coming to the PAM4 systems, for PAM4 transmitter, we have the digital to analog converter. The DAC is a simple binary weighted capacitive array, and the capacitive switching is the key component of power consumption. Assuming the equal probabilities of zeros and ones, the power of DAC is given by this expression. The current mode driver consists of two binary weighted current sources of tail currents, one IT and 2 IT, and its power is given by this expression 3 VD times IT. The receiver is an analog to digital converter. For the ADC, we use a 2-bit flash ADC consisting of 3 comparators. The power of matching limited comparator given the oxide capacitance Cox, threshold voltage mismatch coefficient AVT, and peak-to-peak input voltage V in peak-to-peak, minimum required capacitance CC min is given by this expression. The encoder here is a VLS encoder or a ones counter comprising of full adders, and its power in terms of a typical gate energy E gate is given by this expression. We calculate the power for NRZ and PAM4 at their highest frequency of operation. As we can see, the energy efficiency per bit for NRZ is 13.32 picojoules per bit, while that for PAM4 is 4.87 picojoules per bit, which makes PAM4 63% more energy efficient. The percentage distribution of power across the various components is shown in the pie chart for both NRZ and PAM4. On the concluding lines, we have model coplanar microstrip lines in HFSS with channel length and pitch as parameters, yielding one touchstone file for each configuration, giving a total of 100 cases to study. Generally speaking, the attenuation increases with increase in the interconnect length, and we also notice that the crosstalk interference is a limiting factor for pitch scaling. We comparatively studied 2 signaling schemes, NRZ and PAM4, to determine the maximum frequency of operation for each of the 100 cases. The maximum frequency of operation, or the Fmax, depends on multiple factors, including the dimensions. The shoreline-BW-density, which is defined as the bandwidth per unit length, is 27% higher for PAM4 for 5 micron pitch. The first order power estimates show that the PAM4 is 63% more energy efficient in terms of energy per bit transmitted. Thus, we have systematically demonstrated through this model study that higher order modulation schemes like PAM4 are promising candidates for short length, fine pitch, chiplet to chiplet interconnects. Thank you.